G'day folks, filming this from home for you, so there might be a bit of background noise you're going to have to put up with that. Looking at exponential equations for exercise 2J. I'm going to be going through some notes. I'll be talking through them. You'll need to pause the video and get the notes down. You'll need to write down what it is I'm saying to you. There's a fair bit to cover, but by the time you get to the end, you're going to pick up some very, very useful tricks for solving these sorts of equations. Okay, so an equation with the unknown in the power is an exponential equation, right? Exponential because another word for power is exponent. So here we've got 3 to the power of x equals 9. Because the unknown is in the power, this is an exponential equation, right? Now some exponential equations like this one are very easily solved just by inspection. Inspection just means just looking at it. So you look at this and you basically ask yourself the question, if 3 to the power of x equals 9, well 3 to the power of what is equal to 9? I mean, it shouldn't be too difficult to realise that 3 to the power of 2 equals 9, because 3 times 3 equals 9. Okay, 3 to the power of 2 means 3 times 3, 3 times 3 equals 9, 3 to the power of 2 equals 9. So that means that x over here must equal 2. Okay, if 3 to the power of 2 equals 9, then x equals 2. Pretty straightforward, right? Well, the problem is that these sorts of equations can't always be solved by inspection, just by looking at it. Okay, so there's an advanced technique that is very, very easy, I assure you, that uses logarithms, right? An advanced technique that is pretty easy uses logarithms, okay? So what are logarithms? Logarithms are the powers that numbers give to a base. And what the heck does that mean? Well, consider this, right? 1 is 10 to the power of 0. Okay, because anything to the power of 0 equals 1. So we say that 1 gives 10 a power of 0. Okay, 1 gives 10 a power of 0. 10 is 10 to the power of 1. So we say that 10 gives 10 a power of 1. 100 is 10 squared, because 10 times 10 is 100, right? So we say that 100 gives 10 a power of 2. So that 100 there gives this 10 a power of 2. 1,000 is 10 to the power of 3, so we say that 1,000 gives 10 a power of 3. And so on and so forth, right? So 10,000 would give 10 a power of 4, 100,000 gives 10 a power of 5, 1,000,000 gives 10 a power of 6, etc., so on and so on. Okay, so here's something I want you to think about. If 100 gives 10 a power of 2, right? So 100 gave 10 a power of 2, and 1,000 gave 10 a power of 3, what would 500 give 10 a power of? Or at least roughly between what two numbers would 500 give 10 a power of? Okay, so if 100 gives 10 a power of 2 and 1,000 gives 10 a power of 3, between what two numbers would you expect 500 to give 10 a power of? Well, I mean, the answer's kind of in the question right there, right? So here we go. Since 500 is between 100 and 1,000, the power that 500 will give to 10 would be between 2 and 3. Now, we can use the log button on our calculator to verify this. Okay, so I want you to use log on your calculator to show that 500 gives 10 a power of 2.69897 to 5 decimal places. Okay. Now, there's more, but I just got bored, so I just stopped at 5 decimal places, right? So what I want you to do is to, on your calculator, press log 500 equals. All right, so log 500 equals, and you should get 2.69897, okay, to 5 decimal places. So your calculator has a built-in base 10 connected to the log button. Right, so you don't have to tell your calculator, oh, by the way, I'm doing base 10. That's built in. Now, you'll need to know this for what we're going to come across later on, okay? Your calculator only works in, or there's another number that it works in, but for now, consider that your calculator only works in base 10. Right? Okay, so what's a logarithm? A logarithm, or a log for short, is a power. So, what's the log of, log base 10? What's the log of 100? In other words, what's the power that 100 gives to 10? It's 2. So log of 100 is 2. So here's an algebra definition of logarithm. Okay, so the definition says that if a equals b to the power of c, then log base b of a equals c. Right, so you write if a equals b to the power of c, then this thing here. The way you read that is log base b of a equals c. Okay, log base c of a equals c. Log base b of a equals c. That's what I said. Okay, so here's an example that we've seen. 1,000 is 10 to the power of 3. So that means that log base 10 of 1,000 equals 3. Okay, log base 10 of 1,000 equals 3. You can check it, right? Press log of 1,000 equals on your calculator, and your calculator should spit out 3 as an answer. Okay, so we need to learn a thing now called the change of base law. Okay, now there's a whole lot of laws that come with logarithms. Come on, focus. There we go. There are a few laws relating to logs that we need to learn, that we will learn rather, in advanced maths in year 11 and 12. But for now, we just need one of these laws, and that law that we need is the change of base law. Okay, so we're very close to the end now. Let's have a look at this change of base law. So the change of base law says that if I've got log base a of b, I can change to whatever base I want. Right? I can go to any base I like. So I'm going to go to base n, right? And n could be any number. So we're going to use base 10, right? Because base 10 is what our calculator does. So log base a of b is log base n of b divided by log base n of a. So the big number goes up the top, and the base number, the little number there, goes down the bottom. And we can have any base there that we like. Right? So this is called, so this thing here is the change of base law. Okay, so let's move on. Okay, so we can combine the definition of a log that we saw above with the change of base law to easily solve exponential equations. Now you're probably thinking, Obeid, you totally lost me here. How is any of this easily solving equations? Well, have a look at this example. So I've got 4 to the power of x equals 32. It's hard to work out what number you've got to raise 4 to the power of to get 32. This is a tricky question, right? Most of you 10 kids would be stumped at this question here. Okay, but let's see if we can't combine what we've already learned to do this. So when we looked at logs earlier, we would write that a number gave a base, a power. So I didn't write, for example, I didn't write 100. I didn't write 10 squared equals 100. Okay, I wrote it the other way around. I wrote 100 equals 10 to the power of 2. Right? So we're going to do that for our problem here. So we've got 4 to the power of x equals 32. I'm going to write it the other way around so it matches up my definition of a logarithm. So I'm going to write 32 equals 4 to the power of x. Right? So that means that we take this number here, that's our base, and we pull it down underneath. Okay, so 32 stays there. We grab the 4 and we pull it underneath, and then the x just comes down here. So 32 equals 4 to the power of x, then log base 4 of 32 equals x. Okay, so we're getting there. So we've got this thing here equals x, and we want to find x. That's good. Our problem is that our calculator doesn't do base 4. But we can use the change of base law, right? Log base a of b, remember? Log base a of b is log base n of b divided by log base n of a. So log base 4 of 32, we're going to go to base 10 because that's what our calculator can do. Log base 4 of 32 is log base 10 of 32 divided by log base 10 of 4. I just stick this in my calculator. Literally, just stick that straight into my calculator and press equals, and my calculator tells me it's 512 or 2.5. Okay, it's that easy. 1, 2, 3, 4 lines to get our answer for an otherwise very, very complicated problem. Okay, so guys, this 4-line method will work for all of the questions you're going to come across in exercise 2J. If there's anything you think it doesn't cover, let me know, and I'll show you what you're missing out on. Alright folks, cheers. Good luck with exercise 2J.